Back. So in the last video I explained to you about some enthalpy changes. So I started that video by explaining you about some what is meant by the enthalpy change or the standard enthalpy change for a particular reaction, and then explained about the standard enthalpy of formation, the standard enthalpy of combustion, and finally the standard enthalpy of boron dissociation. So I finished talking about the factors that affect the standard enthalpy of boron dissociation or the median boron dissociation energy. So in this video I will be talking about some more enthalpy changes, and those all fall under the category of standard enthalpy of a particular reaction. So the first enthalpy change that I will be talking about in this video is about the standard enthalpy change of neutralization. So as I mentioned already in my last video, we denote the value delta H net phi here or delta naught here 0 here, so that represents that this is the standard enthalpy of neutralization for a given reaction. We can distinguish that from the other enthalpy changes. So the standard enthalpy of change of neutralization, as its name implies, explains about the neutralization reaction for a particular chemical change. Now you know what is meant by neutralization. So neutralization involves an acid reacting with a particular base and formation of liquid water, or liquid water means liquid H2O, right? So the enthalpy change for a basic reaction, such a basic reaction, is that H plus ions in the aqueous phase reacts with OH minus ions in the aqueous phase to form H2O in the liquid phase. So the energy for such a reaction is calculated as minus 57 kilojoules per mole. Now for most of these gases, for most of the acids, and for most of the acids which have one hydrogen, for example HCl, HNO3, even HPO4, right? So various acids which have one hydrogen or unihydrogen gases, unihydrogen acids and unihydroxyl bases, for example NaOH, KOH, and even you get various acids, you can form various acids which have one OH in their one OH compound in their total compound. So when such an acid and a base reacts and forms water, the general enthalpy change for such a reaction is calculated as minus 57 kilojoules per mole. And what's important and what's interesting here is that furthermore you can divide the delta H net or the standard enthalpy of neutralization that you define for a general reaction like this into that of an acid and that for a base. So in general, we define the standard enthalpy change of neutralization for a particular reaction as the enthalpy change that occurs when a mole of H plus ion, or when this is 1 mole of H plus ion, so you know that the coefficient here is 1, in an aqueous solution, so it should be in the AQ mode, reacts with a mole of OH minus ions. So again the coefficient here should be 1, and that should also be in the aqueous solution or in the aqueous mode, and they should be in the standard state, and that should form a mole of H2O. So all these should be 1 mole, and the enthalpy change for such a reaction is defined as the standard enthalpy change of neutralization. So as I mentioned a little while ago, the standard enthalpy change of neutralization for a general reaction can be diverged to two individual parts as the standard enthalpy change of neutralization for an acid and that for a base. Now when I explain about the standard enthalpy change for a neutralization of acid and that for a base, you should always distinguish the differences between what I explained you. Now in the case of the standard enthalpy change of neutralization of an acid, it's actually the enthalpy change that occurs when a mole of H plus ions in an aqueous solution, so it should be an aqueous solution and it should involve an acid because it should provide H plus ions or hydrogen ions, and it should react with a strong base in an aqueous solution under the standard state to form a completely neutralized solution. Now you know that when H plus ions react with OH minus ions, it forms H2O. But now in the case of this reaction, in which you have hydrogen fluoride and sodium hydroxide, this fluoride ion and the sodium ion should also form another compound in order for this reaction to be balanced, right? So you know that the coefficient here should be 1, this coefficient here is also 1, and you form 1 mole of hydrogen. So the standard enthalpy is minus 68.6 kilojoules per mole. But now you may question that I defined that to be minus 57 kilojoules per mole, but that is actually due to the formation of H plus ions with the OH minus ions. The H plus ions and the OH minus ions react to form H2O. But you know that there are also compounds in which we have fluorine and higher actually sodium. You should break that bonds and then you should form sodium fluoride as well. So some energy is dissipated for such a reaction. So finally you don't get that minus 57 for most reactions. For reactions involving compounds, for a base and an acid, you will get a value that is different from the general value of minus 57. So in this case you get minus 68.6. But in the case of A2SO4 and KOH, what generally happens is that you know that A2SO4 is a strong acid as well as KOH is a strong base. So they both form K2SO4 and 2 molecules of water. So that's actually twice the value of the general expectant value of a reaction involving acids and bases. Now it's actually minus 57 times 2, that forms minus 114 here. So for strong acids and strong bases you will get that minus 57, but for weak acids and weak bases you will not get that. We don't actually consider about the weakest acids or the weak acids and the weaker bases. I don't mean that they are very weak, right? They are not very weak, but compared to some other acids they may be weak, but they are not very weak, right? They are somewhat strong in their acidic or the basic nature, but depending on their strength of acidity and the strength of basicity, what generally happens is that there is a simple deviation from the expected minus 57 or an integer multiple, as in this case, of that minus 57 kilojoules per mole. So that generally is depends upon both the behavior of the base and that of the acid. Now when considering of bases, as I mentioned, you can also define a standard enthalpy change of neutralization for a base. So that's very similar to the definition and the examples and the reactions that happen when I define the standard enthalpy change of neutralization for an acid. So it's defined as the enthalpy change that occurs when a mole of OH minus ions or hydroxyl ions in an aqueous solution, so it should be in aqueous mode. You know that sodium hydroxide here and barium hydroxide, all those are in the aqueous mode, reacts with a strong acid in an aqueous solution. So HCl is in the aqueous mode here. Here also HCl we have in the aqueous mode, and the total solution should be also in the aqueous mode, and they should be under the standard state, and they should form a completely neutralized solution. So sodium chloride is a neutralized compound, barium chloride is a neutralized compound, water in its liquid state is also a neutralized compound. So the total reactants, the total products make a complete neutralized solution. So you can define the enthalpy change for neutralization as the standard enthalpy when it is in the standard state as follows. So in the case of sodium hydroxide and HCl, you get the general minus 57.3, which is just a little bit deviating from the expected minus 57, about 0.3 deviating in fact. And for barium hydroxide and 2HCl, since the coefficient here is 2, you get twice the expected value. So that's it about the standard enthalpy of neutralization. You can write infinite number of standard enthalpy of neutralizations because you have infinite number of acids and bases. We generally consider about the strong acids and strong bases, not the strongest but not the weakest, but a little bit strong, right? So infinite number of reactions can be written, and the general expected answer for such a reaction is minus 57 kilojoules per mole, or an integer multiple of minus 57 kilojoules per mole. So that's it about the standard enthalpy of neutralization. So the next thing that I'll be discussing here is about the standard enthalpy of solution. So standard enthalpy of solution, as I have been discussing all these standard enthalpies, is denoted by a special symbol which involves SOL symbol. So delta H SOL phi or delta H SOL naught denotes the standard enthalpy of solution for a particular chemical reaction. So standard enthalpy of solution involves dissolving, right? Dissolving actually the gaseous ions. When a mole of gaseous ions in the standard conditions changes into the solution form in the presence of an excess solvent. Now we dissolve. Now for example, you take this example, sodium chloride. We dissolve sodium chloride in some aqueous solution to form sodium chloride aqueous mode. Now sodium chloride is initially in its solid state. When you dissolve in an excess of solvent, you form the aqueous solution NaCl aqueous. So the reaction, the general reaction for such a process is that you take the ions here. So the ions involved in the sodium chloride bond are the sodium plus ions and the chloride minus ion. So sodium plus ion dissolves in an excess solvent to form sodium plus solvent or sodium plus aqueous. So you get that here. And the chloride minus ion dissolved in the excess solvent to form chloride minus solvent here. So you get the chloride ion here. So these two compounds form the standard enthalpy of solution when you subtract the enthalpies. And in the case of sodium chloride, you get that value to be plus 5 kilojoules per mole. So that's just a simple standard enthalpy, like the standard enthalpy of formation, that doesn't involve many steps or many complex important points. So the standard enthalpy of hydration, which I'll explain now, is also another simple standard enthalpy. So these are actually just definitions, but they are important in one concept which I'll be discussing in the last video of this series of videos. So you'll come across, you will summarize all those in one energy diagram. So these should not be just isolated as just standard definitions. They should be memorized in some practical and useful manner. So the next enthalpy I will be talking about is the standard enthalpy of hydration. So standard enthalpy of hydration explains that the enthalpy change that occurs when a mole of gaseous ions under the standard conditions changes into the solution form in the presence of water. It's all about hydration or meeting with water. Some ion, for example sodium here actually is dissolved in water, and that forms sodium plus aqueous ion. So now you can also say that the standard enthalpy of solution here has somewhat of a standard enthalpy of hydration. So hydration, and we denote that by delta H5 HYD. Now in the case of sodium, we denote that to be sodium plus gas. So it's in the gaseous mode because we take 1 mole of gaseous ions, and it should be in the standard condition. So it's already in the standard condition, and it changed into the solution form, which is Na plus aqueous in the presence of excess water. So water is in the liquid state, and the enthalpy for such a reaction is exothermic, or delta H is negative, and we have measured that to be minus 405 kilojoules per mole. What's important here is that when the size of an ion decreases, now for example when you compare sodium and magnesium, the ion dipole attraction between the ion and water increases when the size decreases. Thus the energy released when forming an ion dipole bond increases. So what generally happens is that when the size of an ion gets smaller and smaller, the negative value of delta H HYD, or the standard enthalpy of hydration, increases. So that's an important point when explaining about the standard enthalpy of hydration. So the next enthalpy is about the standard enthalpy of transition. So transition is actually important in the case of allotropic forms. Now for example, if you take carbon has many allotropic forms. For example, you have carbon in the form of graphite. You also have carbon in the form of diamond. So graphite and diamond are both compounds of carbon, but they are allotropic forms. You can say that the carbon in the graphite mode is completely equal or completely identical to the carbon in the diamond. Although the carbon atoms are same, the total bond or the system or the unit as a whole is not identical. So those are called allotropic forms. If they are different, if they exhibit different physical characteristics, shapes, chemical characteristics, and other conditions or the behavioral patterns within the same molecule of an element. So those are called allotropic forms. And the enthalpy of transition between these the enthalpy of changing between these allotropic forms is called the standard enthalpy of transition. So it's the enthalpy change that occurs when a substance under standard conditions, so carbon should be in the standard form, gets converted from one phase to another phase of the same substance. So that's it about the standard enthalpy of transition. So the final enthalpy that I will be discussing in this video is the standard enthalpy of dissolution. Now you know what is meant by the standard enthalpy of hydration. Yeah, explained here. You know what is the standard enthalpy of solution. So these are actually analogous to the standard enthalpy of dissolution. So they just have some a small difference between them, right? Small difference between them. They are almost analogous. So you define the standard enthalpy of dissolution to be the enthalpy change that occurs when a mole of a substance under the standard conditions is dissolved in a solvent to form 1 cubic decimeter of a solution. For example, if you have sodium chloride here, you dissolve in some aqueous solution. So sodium chloride is initially in its solid state. You dissolve it in an aqueous solution to form sodium chloride aqueous, and that energy required for the standard enthalpy of dissolution has been measured as 1 kilojoules per mole. Right? So those are the standard enthalpies that I will be talking in this video. So in this video I explained to you about some examples in which we have different standard enthalpies, and also explained about these definitions using practical examples. So I'll be continuing these standard enthalpies of formation, and I'll actually conclude the standard enthalpy of formation in my next video. So thanks for watching these videos, and I hope that you will join with me to explain to understand about the different enthalpies in the next video as well. So finally, thanks for watching this video, and see you then.